Okay, in this lecture we're going to start out with a few different somewhat random things but related practical applications in symmetry, and we'll go through a number of items related to, for symmetry, then mesh density, things like stress concentrations from a crack, and then in the following video I'll finish this lecture with a couple of examples. So what we do here is we start out with an example in symmetry where over here you have a rod. There may be heat transfer along the center of this rod in the radial direction, and you may also have variations in convection along Z. So here's our definition of our radius, a radial heat transfer. You've got a theta, but we're going to define this as theta independent or axisymmetric. And the ODE that governs this heat transfer, so here's the radial heat transfer. Here is the variation in heat transfer effects in the Z direction. And here's some kind of source term. So we define our vector, our heat transfer, or our flux, as a variation in the I and J direction given here, which corresponds to the radial and the Z direction. Okay? So our unit normals are again in radial and Z. So we can take this ODE, or actually PDE, and put it into a weak form. So we multiply by a scalar weight function. So note, we just have one variable t, so all you need is a scalar weight function. And we use product rule on the radial derivatives. So substituting back in, we get a relation that looks like this. You can do something very similar on the Z term. I just haven't written it down, but it's the same as our ODE problems. And after that, we get it in the final form, given here, and then simplify this down by taking an explicit derivative on the last term, and that gives this flux on the boundary. So again, you have to be careful if there's convection. So here's your convection term. So this is the effective heat transfer that includes both conduction and convection, and that gets substituted in. Okay? Alright, so that's just one example on how to set up an axisymmetric problem. Here's a few other things to consider when you're setting up these type problems. So let's say if you have a plate with a circular hole in the center. So if you're uniaxially loading this, you have quarter symmetry, so you don't have to solve the whole thing. You reduce the computational intensity and only solve 1/4. So that means that this is constrained in the x direction on this plane, and on this edge it's constrained in the y direction. Now, if coming back to this axisymmetric case, if you have biaxial loading with equal magnitudes in x and y, then it's axisymmetric, and it becomes a simpler problem. So, if you look in Chapter 9 of Reddy's book, they talk about other modeling considerations, and this is mainly an introduction on. I'll give an example or two later on in the next video, but first to introduce this concept of going from a global xy coordinate to this local z eta coordinate. Reason we do this is due to the fact that you may have a complex geometry in your xy coordinate, and if you map this from your true xy coordinate on some complex geometry to a local normalized coordinate. So you basically taking a quadrilateral and mapping it to a unit square. So you notice this is plus or minus 1 on the coordinates for z and eta. What we do is we do all our integration. I'll show later you have to determine quadrature points. We don't explicitly integrate these weight functions in 2D. We do an intermediate step to make the mathematics simpler so it can be implemented numerically. So through this mapping you get a relation between not only x and y and z and eta, but also the derivatives, where you have to compute the Jacobian. And this Jacobian is given in this form. We'll go into more depth on where this comes from, but it basically relates the change in x with respect to local coordinates, change in y and local coordinates, etc. One issue is it must be well defined. Okay, meaning that if you take the determinant, it better be greater than 0. If it's not, you're going to run into problems because you often have to invert it. So here are physically places where this will give you problems. If these angles are too big on a quadrilateral, or here if you have angles are too small, basically these areas are starting to go to 0, and that leads to a determinant that may be close to 0. So as a rule of thumb, you typically want to try to keep these angles around 15 to 165 degrees to avoid these things. In COMSOL, there should be ways to check the forgetting the exact term, but ways to check to make sure your determinant is not approaching 0, such that you don't run into these numerical issues. Alright. Sometimes you want higher order elements with multiple nodes, but then in some areas you may only need a linear interpolation function. So here there's a transition element node. So on this side you're transitioning from this quadratic element to a linear element on this side. So that's what this does. Other thing is, we've talked about mesh refinement. If you have a contact point, there's going to be high stress concentrations here, so you can need a lot of elements. Sometimes what we do is we'll approximate contact boundary conditions with a distributed load, in this case, to try to avoid some of those issues. It really depends on the problem you're solving. If you're really interested in stress concentrations or impact, you may need mesh refinement. If you're more interested in global stresses out here, you may be able to smear out the local stress concentration. Another interesting thing is fracture mechanics. So if you have a crack, theoretically an asymptotic crack has a stress that's 1 over square root r. R is your radius from the crack tip. So if you want to simulate this singularity in a linear elastic material, if you have triangular elements and you move the node to the quarter point, that automatically gives a singularity at this point, at the crack tip. So I've moved this to the quarter point, and that will give me singularity at this point. So here's why. So basically, if you were to start with a quad element and compress this down to a triangle, and then move these points from the center down to the quarter point, we'll talk some more about this later, but basically on eta equals 0, that means you're moving along this x-axis. It can be shown that x is related to your local coordinate z in this form, and when you solve for z, you have an equation that looks like this. So you notice as this goes to 0, you've got this square root x term, and when you take derivatives, take a derivative on your displacement, this is proportional to your strain, and that ends up with a 1 over square root x term, which then leads to a effect of a stress singularity in terms of 1 over square root r. So that's where this comes from in this case. So there's things you can do with playing with your interpolation functions. And I think we're gonna stop there and do examples next time.